So it's lecture 26. Okay, so yeah, lecture 26. And it's the last lecture per se on differential equations, although they'll come up sort of in a sort of secondary way in the last two lectures as well. So last time, we discussed systems of linear ODE. Which was a system of differential equations that looked like this, right? D by dt of some vector valued function x is equal to a times x of t, where a is an n-by-n matrix, and x of t is an unknown vector valued function with n components, each of which is infinitely differentiable. So this is some fancy sort of pretentious notation for that, right? So this is saying infinitely differentiable. And this is saying that there are n components, or it's an Rn valued function. So we said what these are, and we had two questions. The first question is find all solutions x of t, and we conceptualized this as a linear algebra problem because this equation here, the key point is that this equation is equivalent to the equation t of x equals 0, where t is a linear transformation from this vector space of functions to itself that just takes the derivative of the function and then subtracts the component-wise derivative and subtracts a times. So I'm going to write it like this, right? So find all solutions, and then this is equivalent in linear algebra terms to finding the kernel. And the second one was solve the initial value problem, which I'll talk more about later. So last time, we said what this is. We defined it, and we stated one important theorem without proof at the end of the lecture, which is the existence and uniqueness theorem for such systems, which says that the linear transformation S going from the kernel of this T, where the T is the same one above, the same kind of operator above, to Rn by S of a vector valued function x is just x evaluated at 0 is an isomorphism. Okay, so maybe just to emphasize, I'll write this x as x of t everywhere, right? Just to emphasize that it's a function. So it just evaluates that function at 0, and that's an isomorphism. So this, implies in particular that the dimension of the kernel is equal to n, right? Because it's an isomorphism. So whatever the solution space is, it's an n-dimensional vector space. And today we're going to discuss three questions. So the first question is how? So how do you find solutions? How to find a general solution. So that's question number one. Then I'm going to talk briefly about how to solve the initial value problem. And then finally, I'm going to tell you why this is so useful. This might seem like kind of a weird thing. It's a system of differential equations. I'll show you in the end that it implies everything we did before and a lot of interesting physical models, so applications and I guess connections. Okay, so that's an outline of the lecture. So any questions before we begin? Okay, so let's start with how to find the general solution. So I'll do it by example. So first, let's see a very simple example. So example 1, here is a system of first order ODE, x1 prime of t equals 3x1 of t, and x2 prime of t equals 5x2 of t. So indeed, you can write this in this sort of fancy format, which is that d by dt of x of t. Now x of t, remember, is this vector whose components are x1 of t and x2 of t, is equal to some matrix times x of t. And what's that matrix going to be? Well, it's just going to be a diagonal matrix, 3, 0, 0, 5. And this is the matrix that's being called A in the previous slide, right? And then, we have this operator t is equal to the derivative minus A. So, okay, we've set up all this fancy notation, but I mean, okay, does anybody know how to solve this system of equations? Let's go back to math 1b.
Take an integral.
You could just take an integral, okay, of what? I mean, okay, the hint is these equations have nothing to do with each other, right? There's one equation in x1, and then there's another equation in x2. And there's no interaction between them. This is just two one variable ODEs. So what's the solution to the first one?
Wouldn't it be e to the 3t? Someone said it in chat.
Yeah, exactly. So these are two, I'm going to say, decoupled equations, which means they have no interaction with each other. So really, you could have done this in math 1b. The solution to the first one is, I'm sorry, there's no vector here. The first one is just an exponential function. But actually, it's any scalar multiple of that, right? That would do. And what about the second one?
e to the 5x.
Yeah, some other constant times e to the 5t, right? And these, we know these are the only solutions. I mean, presume you can also do it by integrating. So what's the general solution?
Wait,
Well,
why would there be a c1 in front of the e3t? Don't we want its derivative to only be 3x1t? So there's no c1?
well, there is, right? Because I mean, let's just check this, right? So
okay, never mind.
yeah, if you multiply both sides by c, it doesn't change anything, right? So yeah, good thought. So what's the general solution? Well, the general solution is, well, let's write it in vector form. So the first component is x1, so that's any c1 times e to the 3t. And the second component is some other c, could be different, c2 times e to the 5t. And in linear algebra terms, you can write that as a linear combination of two vectors. So what's the basis for the kernel of T?
E to the 3t and e to the 5t, those two vectors.
Right, but you didn't fully specify the vectors.
Oh. Span.
Well, okay, so what I'm looking for is that the e to the 3t is in the first component here. and 0 e to the 5t, second component. Yeah. Okay. So this is kind of, in a way, trivial because these are decoupled, you don't really need to do anything. You just solve the scalar ODEs. It's really not a system. The equations have nothing to do with each other. So this is easy. But any questions about this? The only tricky part is that maybe you're not familiar with vector valued functions. So I'm expressing the solution as a vector valued function. That might be the new thing. But any questions? Okay, let me show you a more interesting example in that case. Let's call this example 2. So you have x1 prime of t equals 2x1 of t minus x2 of t. x2 prime of t equals 3x1 of t minus 2x2 of t. And this is a bit non-trivial, right? Because these equations interact. So the word that's often used in physics and other areas is that these are coupled. This is not, you cannot split it into two, single equations that you can solve separately. Now in our fancy notation, how do we write this? Well, this is just x d by dt of x of t equals this matrix times x of t. And the matrix has entries 2, minus 1, 3, and minus 2. So this matrix is called, this is the matrix we're calling A. And then, of course, we have T, which is equal to d by dt minus A. And we're looking for vectors in the kernel of T. By the way, what's the dimension of the kernel of T going to be?
2.
2. Exactly. It's going to be 2 because of this theorem, right? The dimension of kernel T is equal to n if it's an n by n matrix. So we're looking for, so now we want to find a basis. So now this seems kind of tough, right? So it's kind of not clear where to start. So the idea here is there some way of turning this into a problem that's decoupled? So the difference between a decoupled problem and a coupled problem can be seen in the matrix, right? Can somebody tell me what special feature the decoupled problem has?
It's diagonal.
It's diagonal, exactly. So decoupled problem corresponds to diagonal matrix, right? So, okay, so well, there's sort of a natural thing given what we learned in the course, right? Which is that let's try to turn A into a diagonal matrix by diagonalization. So reduce to diagonal case by diagonalizing A. So let's diagonalize A, right? Okay, so what's a characteristic polynomial? Okay, it's this, I guess, which is, I guess, minus 2 minus t, oh, sorry, minus 2 plus t. Okay, let me just write this out. Which is 2 minus t times minus 2 minus t plus 3, which is, oh, sorry, have I got this right? Yeah, which is minus t squared minus, or sorry, this is just t squared minus 4 plus 3, which is t squared minus 1, which is t minus 1 times t plus 1. So the eigenvalues are lambda 1 equals 1, lambda 2 equals minus 1 eigenvalues. And you can do row reduction, which I'm not going to do, but I did it at home or whenever. And you get eigenvectors 1, 1, and 1, 3. Okay. Okay, so now we have these. So how are we going to use this to solve the equation? Well, the key insight is that A, what's the nice property of eigenvalues and eigenvectors, right? So the property is that A v1 equals lambda 1 v1 and A v2 equals lambda 2 v2, right? That's what it means. And what that means is that, if you look at functions that are multiples of the eigenvector, then multiplication by A is just going to become multiplication by a number. Okay, so let me write this out explicitly. So key idea is to consider the function, let's call it x1 of t, to be e to the lambda 1 of t times v1. Okay, so let that sink in a little bit. That's a vector valued function of the variable t. So writing it explicitly, so lambda 1 is 1, right? So it's going to be e to the t times 1, 1. So this is the function e to the t, e to the t. Okay, so this is the key idea. And now the beautiful thing that's going to happen is if I look at what the equation does to this type of function, it's going to turn into a one-dimensional problem because of the eigenvector equation. So what's the upshot? The upshot is, well, the equation up here is ax equals x prime t, right? That's the equation we're trying to solve here. So let's see what happens, right? So a of this x1 of t is a times e to the lambda 1 of t v1, right? Which e to the lambda 1 of t is just a number, e to the lambda 1 t is just a number, and so now you have a v1. So what simplification can I do now?
We can get rid of the A and just put in the eigenvector there. Or
Yeah,
not, eigenvalue, sorry.
Exactly. So this is what was special. Because of the eigenvector property of v1, this just becomes a number now. And that number is lambda 1. So this becomes lambda 1 e to the lambda 1 t v1. And anybody see how to relate this to the derivative of x1 of t?
This is the same thing as like if you differentiate e to the power of lambda t v1.
Exactly. So
right?
This is the derivative of e to the lambda 1 of t times v1. I can just throw the v1 in there because it's a constant, right? It doesn't depend on t, right? v1 is a fixed vector. But that's it. That's the solution to the equation, right? Equals d by dt of x1 t. So these eigenvectors, the magical step was this step, right? Turned a matrix problem into a scalar problem, right? So this turns, it turns it into a 1D problem, right? Because it turns a matrix into a scalar. Right? So okay, so the upshot is that this e to the lambda 1 t v1 is a solution. So in particular, it's in this kernel of this operator t. Okay, so any questions about that?
How did you get the equation in the red box?
So this required some ingenuity, right? So I said, let's just consider this function, right? I'm looking for a function. So the rationale behind doing that would be, well, my equation looks like x prime of t equals ax of t, right? And the tricky part is the a, right? The a is mixing up all the entries of x. So what I'm doing here is I'm saying, well, if I just look at a very special class of functions that are multiple of eigenvector, then a will become simplified. So that's how I got to the red box.
I see. Thank you.
There's a way to derive this mechanically if you just write A equals PDP inverse, but it's a bit more pedantic. I think this is more sort of conceptual. Any other question?
So the other answer would be E lambda 2 TV2.
Exactly, yeah, exactly. So similarly, by the same argument, x2 of t equals e to the lambda 2t v2 is also in the kernel of t. And I mean, okay, we'll check that these are linearly independent in a moment, but they are. And so the conclusion is that the kernel of t, because it's two-dimensional, is just the span of these two things, which, you know, are very explicit, right? So in this case, e to the t, and the second one is going to be e to the minus t, 3e to the minus t. Okay. So similarly, okay, I mean, you have to do this as well. So these are the two statements. And then we have the kernel. And we know it's equal since the dimension is equal to 2. So this is kind of a beautiful thing that happens, that you have this coupled system of equations, but the eigenvectors tell you how to decouple it, right? Because after all, what calculus did we do here? We did single variable calculus. We just differentiated this exponential, right? Which is a one-dimensional problem. And so sort of the conceptual point is that when you look at functions that are multiples of the eigenvectors, matrix multiplication reduces to scalar multiplication. And so you get a bunch of one-dimensional decoupled problems. So diagonalization can decouple a coupled system of differential equations. And this is, I mean, this is very useful. So let me summarize this in a theorem. Sort of a general theorem. So if A is a diagonalizable matrix, with real with eigenvalues that are all real, they don't have to be distinct, and eigenvectors, corresponding eigenvectors v1 through vn, which are in Rn, they're of course linearly independent. Then the kernel of this operator d by dt minus a is equal to the span, is always equal to the span of e to the lambda 1t v1 all the way up to e to the lambda n t vn. So diagonalization actually just straight up solves these equations for you. Like if you know the eigenvalues and eigenvectors, you know the solution. I'll say more about physical implications of this later. Okay, so it's kind of a very nice generalization of the first order single variable ODE where the solutions are exponentials. In this case, the solutions are exponentials given by the eigenvalues times eigenvectors of the underlying matrix. So, you know, conceptually, diagonalization decouples decouples the system into 1D problems, decouples the system. So, okay, any questions about the statement of the theorem? And the proof is really just this one line, this very important line where it says upshot, right? That the A just turns into multiplication by lambda 1, and then you just get a one-dimensional differential equation which you can solve.
Does this work if the multiplicity of each eigenvalue is more or greater than 1?
Absolutely. All you need is a basis of eigenvectors. So, I mean, okay, you're kind of getting at my next question, which is, it says here the kernel is equal. So there's this kind of a hanging question, which is, why are these things even linearly independent? Linearly independent in which vector space? They're functions, right? Linearly independent in this vector space. So, so yeah, if there's multiplicity, this still works, and we'll see why in a moment. But to see why, let's try to answer this question. So why are they linearly independent? Well, let's look at this, right? Let's assume they were linearly dependent, right? So if dependent, then you follow the definition, right? Then this happens, right? Sorry, Vn equals 0 in the as functions, right? So this means that this is an identity that's true for every t. Now I'm trying to claim this is impossible, right? Why is it impossible? So for some C1 through Cn, not all 0. So what's wrong with this statement? Why can't this happen? So remember, I've assumed up here that these eigenvectors are linearly independent. That is important. So I got to use that somewhere. So why does linear independence of the eigenvectors give me linear independence of these functions? Can anybody think of a reason?
If you divide by e to the lambda t, which should all be positive, then you should get the equation that C1 V1 C1 or C2 V2 equals 0.
Well, so that's it's close, but it's a little tricky because the lambdas are different, right? There's a lambda 1t and then there's a lambda 2t. So which one are you going to divide by?
Oh, that's a good point. Sorry.
The t equals to 0, and then you'll see C1 and C1 V1, C2 V2,
Yeah.
and Cn. Yeah, that should be.
Yeah, so actually dividing can be made to work, but the easiest way is just set t to be equal to 0. You can do that, right? This is an identity of functions. So in particular, it's true for every t, right? When you set t to be 0, you get C1 V1 plus C2 V2 all the way up to Cn Vn equal to 0. These are now just vectors in Rn. And what's wrong with that?
Then that would mean that V1 to Vn are linearly dependent, which would contradict.
Exactly. So impossible, since V1 through Vn are linearly independent. And so the conclusion is that these vectors are linearly independent, right? Because if they were dependent, then something impossible happens. So that explains why, because you have n linearly independent functions, and you know the dimension of the kernel is n, that has to be all of them. And that's why you get this equality in the general theorem above. So any questions? So I hope this answers the question about multiplicity. There's no problem with multiplicity as long as you have enough eigenvectors, right? So diagonalizable is the key. Any questions about this theorem?
Why can we use existence and uniqueness theorem to just prove this? To just prove they're linearly independent?
Right. So existence and uniqueness theorem says that. Oh yeah, you can use that too. Sure. Yeah. Okay. Yeah. In some way, I actually just proved half of the existence and uniqueness theorem. But yeah, you're right. This is the existence. This is the S map, right? You just set to 0. So it also follows from existence and uniqueness theorem.
Okay, thank you.
In fact, I kind of just proved half of it here. Okay. I mean, why did I set t equal to 0? Well, because that needed some cleverness, right? Because I wanted to relate linear independence or linear dependence of these functions in C infinity R to the n to linear independence of the vectors v1 through vn and rn. And so one way to do that is to set t equal to 0. But it's also what follows in the it's also the map in the existence uniqueness theorem. Any other question about this? Okay, so that covers the case when you have diagonalizable matrix with real eigenvalues. But as we know, in a lot of interesting cases, you have complex eigenvalues. So let's briefly discuss what happens with complex eigenvalues. Okay. When this matrix A has complex eigenvalues. So let's just let's look at an example first. So here's the example. This equals our favorite matrix with non-real eigenvalues times x, right? So this t is equal to d by dt minus a, the underlying differential operator, and a is this matrix. What are the eigenvalues? Well, the characteristic polynomial is t squared plus 1. A has eigenvalues lambda 1 equal to I, lambda 2 equal to minus I, which are complex. And eigenvectors now live in C2, 1 comma I, 1 comma minus I in C2. Now, this is going to be a little bit, this should be familiar. We're going to do basically what we did with second order ODE. So this is good because, can easily check that e to the lambda 1t v1 still satisfies the differential equation, right? Because, okay, you can just, okay, I guess you can just check it, right? D by dt. They're complex, but it still works the same way, right? Equals lambda 1 e to the lambda 1 t. Sorry, that should be a 1. v1, which equals e to the lambda 1 t. Now you group the key. I'm kind of doing the same computation I did last time backwards. It's the same. You group these together, you get that this is a v1 equals a times e to the lambda 1 t v1. So solves the equation. So what's the problem? Can anybody tell me what the problem is?
Lambda 1 is complex.
Yeah, this is not a real function. Okay, we do the same thing that we did last time, right? So we have two of these things, right? We have e to the lambda 1 t v1 and e to the, we have its, so we have two solutions, right? So let me write down so in fact we have two solutions, which are, let's call them, e to the lambda 1 t v1 is one solution. And the other solution is actually its complex conjugate, e to the lambda 2 t v2, which is actually just the complex conjugate of the first one. Okay, this is getting a little scrunched. Let's just, the second one is equal to the complex conjugate of the first one. Okay, I mean, you can see that everywhere, right? So lambda 2 is equal to lambda 1 bar. And because the matrix is real, this will always happen. V2 is equal to, okay, I don't know what color this is. V2 is equal to V1 bar. So bar just means you take complex conjugate of every entry in the vector, right? You flip the I to a minus I. And so these facts actually show that these functions are just complex conjugate of each other. This is what always happens. So now, okay, we're gonna do the same trick, right? We're gonna sorry, somebody asked a question. Can you ask that? I'm not sure I understand the question in the chat. Could you ask it by speaking?
I was wondering if you were adding e to the power lambda 1 tv1 to e to the power lambda 2v2. Or I'm not sure what you did there to get an equal sign and then e to the power lambda 1 tv1.
Oh, I took a complex conjugate. So let me remind people what complex conjugate is. If you have a complex number, a plus, or let's say alpha plus I beta, then its complex conjugate is equal to alpha minus I beta, where alpha and beta are real. So what I'm claiming is that, you know, these two functions that I get are actually complex conjugate of each other. Because, you know, lambda 2 is lambda 1 bar and V2 is V1 bar.
Oh, okay, thank you.
Yep. So now I'm going to do the same trick, which actually, let me just highlight it on this example of numbers. If you take a number, a complex number, and add it to its complex conjugate, and divide by 2, well, the imaginary parts cancel out and you just get the real part, right? Any questions about that? Okay. And similarly, if you, I mean, okay, I guess these boxes are getting a little small here. Similarly, if you take a number, a complex number, and subtract it from its complex conjugate and divide by 2i, what do you get?
Beta.
Beta, which is the imaginary part. Sorry, this is not real part of alpha. This is real part of the complex number, real part of. And this is the imaginary part of alpha plus I beta. So I'm actually just going to do exactly what I did last time, which is add and divide by 2 and subtract and divide by 2i. But I'm just conceptually explaining it in a different way this time because, I don't know, it's good to have two different explanations for the same thing, in my understanding. And plus, this is something you need to know in general. So the same trick is, well, okay. You know, I have that this t of e to the lambda 1 t v1 plus e to the lambda 2 t v2 is equal to 0, right? By linearity, I know that because I found these two solutions. But and I can divide by 2, but this is equal to t of the real part of this. But okay, I mean, maybe I'll just be very concrete, right? So I'll just write down what these are. So, okay, so I have real part of e to the it times 1, e to the it times I. Right, because that's what e to the lambda 1 t times v1 is. Right, just look at what they are here. Any questions about that step? But now, okay, I'm going to remember my other fact about complex numbers. What's e to the, what's e to the alpha, or, or just what's e to the I beta times t?
Sine.
Cosine beta t plus I sine beta t. That was property 3 from last time. So now we have to take the real part of these entries, right? So what's the real part of the first entry of this vector?
Cosine beta t.
What's beta in this case?
1.
Yep, cosine t. And now I times e to the it. So you have to multiply that by I. And now look at the real part of that. Well, if you multiply I sine t by I, you get minus sine t. So the real part is minus sine t. So let's stare at that for a moment. Any questions about that?
Wait, could you quickly re-explain why it's negative sine t again?
Sure. So let's do a little calculation on the side here. Well, you have I times cosine t plus I sine t, right? So that's I cosine t plus I squared sine t, which is minus sine t. So the real part is minus sine t.
Okay, yeah, that makes sense. Thanks.
Yep. So, okay, so what's the conclusion? Did we find a real solution to the equation? Who thinks this is a real solution to the equation?
I do.
Okay, yeah, it is, right? It's a real function. This is a legit real function that's in the kernel of this t, which is what we wanted, right? So, right, this equation is the same thing as saying t of x equals 0. And so this is a legit real solution. Let's call it x1 of t. So similarly, if you take the imaginary part, you get the other one. Right. So in the first one, in the first case, you do addition or the real part. In the second one, you do subtraction or the imaginary part. So e to the lambda 1t v1 minus e to the lambda 2t v2 over 2I. This equals 0, which equals t of the imaginary part of the same thing. So you have e to the it, I e to the it, which now, okay, the imaginary part, so this becomes t of, I guess the first one was sine t, and the second one will just be cosine t. And so this is another real solution.
Is there a name for sets of solutions that are functions?
Yeah, there is, and I'll tell you what it is in a moment. It's used in the book. But it's just I mean, this is a subspace, right? It's a subspace of a certain vector space. But yeah. So anyway, in this case, what's the conclusion? The kernel of T is the span of these two functions. So cosine T minus sine T, sine T, cosine T. If you combine these two solutions, you get, so on this side you took the real part, and here you took the imaginary part. Okay, so a lot of stuff happened in this example, but this example pretty much contains everything you need to know about what to do with complex eigenvalues. I'll articulate it in a theorem on the next slide. But any questions about this? The same as what we did. Yeah, please go ahead.
Oh, sorry. Can you explain why you did plus for the real and then minus for the imaginary? Like.
Yeah. So because look at just what you do for numbers, right? So when you take this should say imaginary part. If you just have a complex number, right? Suppose you want to take the real part, then you add it to its conjugate, right? And divide by 2. Whereas if you want to take the imaginary part of a complex number, you subtract its conjugate from it and divide by 2i. Right?
Yeah.
So the reason I'm writing it this way is to show you that when I take this, I still get a solution of the equation, right? Because if I add 2 solutions of this equation, I get another solution because a set of solutions is a subspace. Because of a linear equation. Does that make sense?
Yeah, thank you.
Yep. Any other question?
So first we had to find complex solutions, and then we derived real solutions from those two?
Yeah, by taking the real and imaginary parts. So I'll summarize it in the next slide. So general theorem about what to do when there are complex eigenvalues. So if a n by n is real and has 2 complex eigenvalues, lambda equals alpha plus I beta, lambda bar equals alpha minus I beta, has complex eigenvalues. With eigenvectors, a plus ib and a minus ib. So by that, what I mean is that, the matrix A times A plus IB. So this is my vector V is equal to lambda times A plus IB. And A times the other vector, A minus IB, is equal to lambda bar times A minus IB. Okay, so these are living in what vector space do these vectors live in?
Complex.
Yeah, Cn. So these live in C. Then the following real functions are solutions to the differential equation. Real part of e to the alpha plus beta plus I beta d a plus ib, and imaginary part of e to the alpha plus I beta a plus ib are real linearly independent solutions of this equation. Now, just to spell it out here, so there's there's a little bit of annoying algebra if you really want to spell out what this is. It's not hard, it's just annoying, but does anybody, who wants me to spell it out? I don't mind, but.
I would like to.
Okay, let's spell it out. Okay, so we just have to expand this, right? So this is the real part of, so there's an e to the alpha t in front of everything. Let's take that out. And now you have a cosine beta t plus I sine beta t, right? That's the exponential. And now you have a plus ib. Okay. So now I have to do some algebra to simplify this. So let's take this down here. So now this is the real part of, you get e to the alpha t, and now you just do the algebra, right? So but you may be a little intimidated because some of these things are numbers and some of them are vectors, but you can multiply numbers and vectors, right? That's just scalar multiplication. And in fact, some of these are even functions, but they're scalar functions, so that's okay. So you get cosine beta t times a plus I cosine beta t times b plus I sine beta t times a, the vector, plus I squared sine beta t times b. Okay, but I squared is just -1, right? So now the real part of this is just going to include the real terms, right? So it's not too bad. You just extract out the real terms. So what are the real terms? What's the real part of this? Somebody tell me.
Cosine beta
Cosine.
t.
Oh, go ahead.
Yeah, cosine beta t and sine beta t. Beta
Yeah,
b.
okay.
Beta t b.
Yeah, and with the negative and with an e to the alpha t. So you have e to the alpha t cosine beta t times a minus e to the alpha t sine beta t times b. So that's what it is. You know, it is what it is. Now, this is not, in my opinion, this is not something you should memorize because it's easy to figure out and it's just algebra. But the conceptual point is you take the real and imaginary part. And as somebody asked in the chat, this is the same, you know, Poincare principle, which is to extract real solutions from complex solutions. Same as what we did for second order ODE. And okay, for imaginary part, I mean, okay. Well, we've actually done the calculation. The imaginary part is the other part, right? So e to the alpha t cosine beta t times b plus e to the alpha t sine beta t times a. So any questions about this general theorem? Why are the two eigenvalues conjugate to each other? So, okay, so question.
Wait, sorry, could we go back a little bit? If not now, then like
Sure.
later.
Yeah, so to repeat the question, in the setup here, in this theorem, I've assumed you have two conjugate eigenvalues, right? And the question is, why is that a reasonable assumption? So let me now answer that. So that's a fact from chapter 5. The fact is, well, if A is real and AV equals lambda V, then you can take conjugate of both sides, right? AV conjugate equals lambda V conjugate. But you may have done this in a homework. That just equals A conjugate times V conjugate. And this, this equals lambda bar times V conjugate. But A conjugate is just equal to A because A is real, right? So we just proved that if lambda is an eigenvalue, then lambda bar is an eigenvalue. So this is a general fact about real matrices, that the complex eigenvalues of real matrices occur in conjugate pairs. So does that answer the question? Okay. So so that's all I want to say about complex eigenvalues and real eigenvalues. So here are two remarks. Remark one, so we won't handle the case when A is not diagonalizable. We will skip the case of A not diagonalizable. It's an optional reading you can read about later. It says pairs, conjugate pairs. You can read about, I think it's section 9.8. You can read about it later if you want. And somebody asked, what are these solutions called? So there's some jargon associated with this whole subject, which I guess you should know because people actually use it later in life. The jargon is if T is one of these operators and its kernel, you have a basis for its kernel, then these vectors are called a fundamental solution set. Now, it's not a new concept. It's just a basis, right? So these n linearly independent functions are called a fundamental solution set. And there's even something a little more, which really is not a new concept, but it's in the book. It's a matrix that's a function of T, which is just a matrix having these things as columns. It's not a complicated thing, but it is maybe your first in your life matrix valued function is called a fundamental matrix. So these are not new concepts. This is jargon. If you see this in the book, that's all it means. Okay. So that's all I want to say about finding general solution of a system of ODEs. Any questions about that before I move on to initial value problem? Okay. The second part of the lecture is about initial value problem. So I'll just do an example. Example is find X, solving, the last example we looked at, d by dt minus 0, 1, minus 1, 0. And now the new twist is has some initial data. Let's say at 0, it's equal to 1. So it's the same thing, but now you have some initial data. Well, you do the same as you did for second order ODE. Step 1, find the general solution. Well, we already did that, right? If you go back to example 3, we found the general solution. The kernel is the span of these two functions, right? These are my x1 of t and x2 of t. So that's a fundamental solution set in this new jargon that we have. And so, okay, let's write that down. So that's all possible solutions of this equation, right? Any questions about that step? Okay, and then the second step is the obvious thing. Step 2, solve for C1, C2 by plugging in 0. So, okay, so what do you get? So you get that C1, now let's evaluate this at 0. So cosine 0 is 1, minus sine 0 is 0, plus C2, sine 0 is 0, cosine 0 is 1, equals, I guess I wanted 1, 1, right? Okay, that's kind of a really trivial system. That's just C1, C2. And so you get that C1 equals C2 equals 1. And so you get the solution x of t equals, in this case, it will be cosine t plus sine t over cosine t, not over, second entry minus sine t. So it's the same, it's kind of the same thing, except you just do it with vector valued functions. I mean, in some sense, you know, this stuff is not that we're doing here is it's mostly just very good practice for becoming comfortable with, you know, the language of linear algebra and vector valued functions and complex valued functions. The underlying, you know, what's actually going on is not particularly complicated or different from the second order ODE case. So any questions about that example? Okay, so let me write down the general method. So to find some x of t in the kernel of one of these operators, which just means a system of ODE satisfying, you know, x of 0 is equal to some x naught, which is a vector in Rn. Well, step one, find the general solution. X of t is a linear combination of some x1 of t through Cn xn of t, which, you know, there are many ways of saying this, i.e. find the fundamental solution set, i.e. find the basis for the kernel. These are all the same, right? And step two is find the specific coefficients, C1 through Cn, which are just real numbers, by solving this linear system. So you have x1 of 0, x2 of 0, all the way up to xn of 0, times these hidden coefficients, C1, C2 up to Cn, equals the initial data x naught. And okay, why is this matrix invertible? Why is this linear system consistent?
Could you use the Wronskian?
You could use the Wronskian. We haven't talked about it, but yeah, it's basically the existence and uniqueness theorem, right? The existence and uniqueness theorem says that this evaluation map is an isomorphism. So if you take, we know that the functions are linearly independent. If you plug in 0, it's just the same thing over and over again. You get something that's linearly independent. So this is invertible by the existence and uniqueness theorem. And if you want to get a feel for it, I'll leave this as a homework. Just check this for the case of diagonalizable A with real eigenvalues. It's sort of a simple exercise. It's almost what we've already done. So it's not really something mysterious. And yeah, okay, more jargon is that the determinant of this is called the Wronskian. But I don't want to really waste too much time on jargon because we're not doing anything very deep with it. But if you see this in life, you'll know what it is. But that's it. It's very straightforward. So any questions about the initial value problem?
Why do we need the existence uniqueness to prove that that part is invertible? Like, is it not enough to just say that because the functions are linearly independent?
Well, okay. So the thing that's missing here is the way I've stated this is this. What I've stated is actually true in general. Is always true. Now, the functions are linearly independent, but in general, that doesn't mean that when you plug in 0, you're going to get linearly independent vectors.
Oh, okay, I understand.
Right? Now, we've in the special case that we looked at in this lecture, like, you know, these exponential functions, it is true. In fact, well, okay. Sorry, we just proved the other direction of that. We didn't even prove that. But yeah, the point is that linear independence of functions doesn't imply linear independence of the vectors you get when you evaluate those functions. That's why you need the existence and uniqueness theorem. But I encourage you to do this homework. So check this, you know, for the case where these functions are, you know, these exponentials. That's very instructive. There you can just kind of see it.
Thank you.
Any other question?
So is the fundamental matrix also the Wronskian? Sorry, I don't know if it's the same thing or not.
No, so yeah, the Wronskian is the
determinant, my bad.
determinant of the fundamental matrix. So
Okay.
yeah, one thing I sort of, yeah. This is all, anything written jargon, you don't have to memorize, or it's just there as a, in case you see the word in the book. But yeah. Okay, so let me finally say a bit about applications. So why did we do all of this? Okay, so the first application is once you can solve systems of first order ODE, you can solve second order ODE. Okay. So let me just show you how. So here's the second order ODE. A is not 0. That's not a system of first order ODE, right? But there's what appears to be a cheap trick to turn it into a system of first order ODE. So this is something I'm going to call the linearization trick, which is actually very important in higher level math. The trick is, well, I have this, you know, I have this equation and it has a second derivative. That's why it's not a first order ODE. I'm differentiating a function twice, right? That's what kind of ruins it. Well, the trick is introduce some new variables. So let's let x1 equal to y1 equal to y, my unknown function. These are all functions, by the way. But now I'm going to introduce a new variable x2, which is equal to x1 prime. Okay. I'm just introducing some new variables. I'm allowed to do that, right? And now I can rewrite this equation with the new variables. So now watch what happens. What is y double prime? Well, that's just x2 prime, right? Because x2 is already x1 prime. What's by prime? Well, y prime is just x2, right? So because x1 prime is just y prime. So this is x2 plus c x1 equals 0. That's a first order ODE. So now what have I done? I've turned this second order ODE into a first order ODE. But it's actually not just that. There are two equations, right? Because there's a relationship between x2 and x1. So I've turned one second order ODE into two first order ODEs. But that's just a system of ODE, right? If I rearrange it, what do I get? I get x1 prime equals x2 prime equals 1 over a, times bx2 plus cx1, or sorry, minus all minuses. This is a system of ODE, first order. So this thing is actually strictly more general. If you can solve systems of first order ODE, you can solve, for example, second order ODEs. And we know how to solve this by diagonalization. So let me just write it in matrix form. So this is x of t, d by dt, equals some matrix times x of t. So the first equation, x1 prime is equal to x2, so I have 0, 1. Second equation, x2 prime is equal to minus b over a minus c over a. This is my matrix A. So I can encode a second order ODE as a system of first order ODE. So this is strictly more general. So any questions about what I just did?
Wait, why do you even need to set like x1 equals y? Why can't you just leave it?
Yeah, you can just leave it as y. I just called it x because in that part of the chapter we're using x as a variable. Yeah, the x1 equals y is not a real equation, right? Because I'm just renaming the variable. Oh, sorry, you're right. You're right. I've got it should be minus c over a minus b over a. I had that wrong. I had the order wrong. So any questions about this? So this seems to give you a different way to solve second order ODE, right? We now have two different ways of solving second order ODE. So the first method is to solve the characteristic equation, right? But now we have a second method, which is to solve the system, this system star. But what happens when you try to solve that system? Well, let's compute the characteristic polynomial. So this is determinant of minus t, 1 minus c over a minus b over a minus t. What is that? Well, that's t times b over a plus t plus c over a, which is just 1 over a times at squared plus bt plus c. So actually, they're not different. It's just that you get the same thing back, right? These are the same polynomial. So it's not a different method. I mean, it's a different way of deriving the same thing. Right? Because in the system of linear equation method, you would find the eigenvalues. But those eigenvalues are equal to the roots of the characteristic equation in the first method. So there's a nice connection between these two things. Any questions about this? This is just conceptual. I mean, in the next slide, I'll show you how you can do something even crazier. Well, okay. The second thing is you can actually solve any higher order ODE. So let's say you have y triple prime minus 5y double prime plus 6y prime plus y equals 0. Why not do the same thing? X1 equals y, x2 equals x1 prime, which is y prime, and x3 equals x2 prime, which is y double prime. So now you write this equation. What do you get? You get x3 prime minus 5 x3 plus 6x2 plus x1 equals 0. And now you have a system of ODE. 1, 2, 3. So this is totally general. Okay. You can solve any differential equation of any order using this method. So that is a very powerful thing. I mean, and it's not just a curiosity. I mean, I'm actually sitting in on a course right now, which is Math 219 or 279 or something like that. And we literally did this today. This is like actually a useful thing. So any questions about this? So it can solve any ODE of any order. By the way, ODE, the ordinary, means one variable, T. So you look at functions of one variable, not of two variables. That's what the ordinary means in ordinary differential equation. And finally, let me bring it back to the original motivation, which is the spring mass system. So let's say you have now two masses. Let's say both the masses are 1. Let's say both the springs have constant 1, just to keep things. Or actually, no. Let's leave the constants to be whatever, and let's assume there's no friction. Or damping. So how do you describe the system? Well, so you introduce some variables. So let's let this be the 0 position, and let's introduce y1 of t to be the position of the first block, and y2 of t to be the position of the second block relative to some 0 positions when both the springs are relaxed. And then what are the equations of motion? Well, let's just write them, right? So the force on the first block is, I'm just going to write it out. You can derive this later if you want, since we're running out of time. But, it's Hooke's law and all that usual stuff. And the net force on the second block is y2 double prime, because the masses are 1, which is minus k2 y2 minus y1. So really, to understand this, you need to solve a system of 2 second order ODE. Can anybody think of how to turn that into a system of first order ODE?
Do the same thing you did previously twice.
Yeah, just do the same thing you did before twice, right? So linearize these. Let's introduce new variables. So x1 equals y1, x2 equals x1 prime, which is y1 prime, x3 equals y2, x4 equals x3 prime. Right? And now these equations, you can rewrite them, because this just becomes, this is just equal to, I mean, okay, let's just rewrite these equations now. So you get x2 prime equals minus k1 x1 minus k2. And then y1 is just x1, y2 is x3. And then down here you get y2 double prime. So y2 double prime is x4 prime equals minus k2, x3 minus x1. And this is a system of 4, 1, 2, 3, 4. This is a system of 4 system of ODE. So even the spring system, which look, I mean, you can do this with any number of springs. Now you begin to see why it's powerful. If you have 100 blocks vibrating on springs, you can write it down in this format, system of first order ODE. And the high level conceptual point is that in general, physical systems can be modeled as systems of ODE using these tricks. And then to really understand what's going on, you need to understand their eigenvalues. So this is why eigenvalues are so important in physics, that vibrational modes of physical systems are always about eigenvalues. So these are, I'll talk more about this later, but that's the physical meaning of eigenvalues, that these are the resonant frequencies. So that's why this is so interesting and useful and ultimately simple, right? You can solve this problem using diagonalization. So this funny thing we learned about diagonalization can solve this huge class of physical problems. And that's, kind of why it's important. So that's it for the lecture. Any questions?
Professor, this is kind of probably going back to probably in last week's lecture, but what does like t equals to derivative of with respect to t minus a mean?
Oh, right. So it means that you have this in the beginning of the lecture. You've written this linear transformation, right? So, right, we have this equation d by dt of x equals ax. That's the same as saying, if I rearrange it, that's the same as saying d by dt of x minus ax equals 0, right? But and then I just define t to be this operator, d by dt minus a.
Okay.
So I'm doing all of this just to write my problem as finding the kernel of a linear transformation.
Okay. Makes sense.
Yep.
Yeah, thank you.
Thank you, Professor.
Thank you.
Hi, Professor.
Oh,
Can we
hi.
go to the slide of application of solving second order ODE? I have a small problem there.
Yeah.
Oh, yeah. So on the left corner, y x a t equals to that of this thing.
Oh, that's not xa. That's the characteristic polynomial.
Characteristic polynomial.
Remember, suppose you want to find eigenvalues of a, right?
Yeah.
Then what do? You write down the characteristic polynomial, right?
Yeah.
So that's what we did here.
Okay, thank you.
Yep.
Thank you, Professor.
Yep, thank you.